There is a house in New Mexico that has been continuously occupied for over 900 years. The walls are still load-bearing. The roof still keeps out rain. The interior stays cool in summer and warm in winter without any mechanical assistance. The material those walls are made from cost nothing to produce. It came from the ground directly beneath the building site. The people who made it mixed it with their hands, shaped it in wooden frames, and set it in the sun to dry. That material is Adobe, unbaked earth brick. And before you decide that is a primitive or regional curiosity, I want to tell you two things. First, there are more Adobe buildings standing on Earth right now than buildings made from any other single construction material. Second, NASA's Jet Propulsion Laboratory published a research paper in 2021 examining Adobe construction as a viable structural system for human habitat on Mars, because no material currently available to a Mars colony better combines structural integrity, thermal mass, radiation shielding, and zero manufacturing energy cost. When the space agency studying how to house humans on another planet looks at the same material a Neolithic farmer in what is now Turkey was using 9,000 years ago, that is not nostalgia. That is engineering arriving at the same answer from opposite directions. I spent the last several months going through the archaeological record, the thermal performance data, and the actual mixing and casting process. What I found is that the reason Adobe disappeared from mainstream American residential construction has almost nothing to do with performance. It has everything to do with the economics of a building materials industry that cannot sell you something you can dig out of your own backyard. So let me show you what Adobe actually is, why it performs the way it does, what the history tells us about long-term durability, and exactly how you can cast your own bricks this weekend with no tools, no equipment, and no material cost beyond your own labor. Part 1. What Adobe is and why it works. Adobe is one of the most misunderstood building materials in common usage, which is remarkable given how simple it is. At its core, Adobe is a mixture of clay-bearing soil, coarse aggregate, typically sand or fine gravel, water, and a fibrous binder, historically straw or grass. That mixture is packed into rectangular molds, unmolded and air-dried in the sun until it reaches structural hardness. No kiln, no firing, no chemical reaction beyond the drying of water from a clay aggregate matrix. The reason people underestimate Adobe is that they confuse softness with structural weakness. Adobe is not soft. A properly mixed and fully cured Adobe brick has a compressive strength of between 300 and 500 pounds per square inch. Concrete block used in residential construction typically falls in the 1,500 to 2,500 pounds per square inch range. So Adobe is not equivalent to concrete in pure compressive load bearing. But the loads imposed by a single-story residential structure, walls, roof, contents, snow, are well within Adobe's compressive range when the wall thickness is designed correctly. The traditional Adobe wall is 18 to 24 inches thick, not the 4-inch veneer of a modern cavity wall. At that thickness, compressive loading is not a design constraint. What Adobe does that almost no other common building material does is thermal mass. And this is where the physics becomes genuinely interesting. Thermal mass is the capacity of a material to absorb, store, and slowly release heat energy. It is measured by the product of a material's density and its specific heat capacity, how much heat energy it takes to raise 1 kilogram of the material by 1 degree Celsius. Adobe has a volumetric heat capacity of approximately 1,300 kilojoules per cubic meter per degree Kelvin, depending on composition. For comparison, wood frame with fiberglass batt insulation has a volumetric heat capacity close to zero. The insulation resists heat flow, but it stores almost none. A 24-inch Adobe wall stores so much thermal energy that it effectively acts as a thermal battery. During the day, it absorbs heat from the exterior environment. The rate of heat transfer through 24 inches of Adobe is slow enough that the heat absorbed at the outer face does not reach the interior face until 8 to 12 hours later, which is to say, the heat of the afternoon arrives at the interior face around midnight, when exterior temperatures have dropped and the stored energy is actually useful for interior warmth. This is called thermal lag, and it is the reason traditional adobe buildings in desert climates maintain interior temperatures between 65 and 75 degrees Fahrenheit year-round without any mechanical heating or cooling, even when exterior temperatures swing from over 100 degrees in the day to below 40 at night. The building is not insulated against temperature change, it is buffered against it. The physics work in both directions. In summer, the wall absorbs daytime heat before it reaches the interior and releases it outward at night when the exterior is cool. In winter, the same wall absorbs solar gain during the day and releases it inward through the night. The R value of adobe per inch of thickness is approximately 0.4 to 0.6. That is lower than fiberglass batt insulation, which runs around R 3.5 per inch. If you compare a 6-inch insulated stud wall to a 6-inch adobe wall, on pure resistance to heat flow, the insulated wall wins. But that comparison misses the entire point. A 24-inch adobe wall has a system R value when thermal mass effects are included in the calculation over a full diurnal cycle that the Department of Energy's Building Technologies Office has estimated as equivalent to R24 to R30 in climates with significant day-night temperature swings. The wall is not just resisting heat transfer, it is managing heat storage and timed release. Those are fundamentally different thermal strategies, and the industry measure of R value per inch was designed for resistive insulation systems, not mass systems. Using it to evaluate adobe is like measuring the fuel economy of a bicycle. Part 2. The 9,000-year record. The oldest confirmed adobe construction in the archaeological record is at the site of Ain Ghazal in what is now Jordan, dated to approximately 7000 BCE. That is 9,000 years ago. But adobe-like earthen construction, hand-shaped mud brick dried in the sun, has been identified at sites going back to 10,000 BCE in the Fertile Crescent. The specific form we call adobe, with its rectangular mold-formed shape and fibrous reinforcement, appears to have been independently developed in at least 4 separate geographic regions: the ancient Near East, pre-Columbian Mesoamerica, pre-Columbian South America, and North Africa. This parallel independent development is significant. When 4 geographically isolated cultures arrive at the same structural solution without contact, that is not coincidence or cultural diffusion. That is convergent engineering. Multiple groups of intelligent people with access to the same raw materials and the same physical problem arriving at the same optimal answer. The optimal answer, apparently, is Adobe. Çatalhöyük in present-day Turkey, one of the best-studied early urban sites in the world, was built almost entirely from mud brick between approximately 7,500 and 5,700 BCE. At its peak, the site housed between 5,000 and 10,000 people in a dense urban environment. The structural system that housed them was adobe. Archaeologists excavating the site found not just the walls, but the internal organization of the buildings, the built-in furniture, benches, sleeping platforms, storage bins, all made from the same earthen brick material. The buildings were constructed without streets between them. People entered through roof hatches and moved across rooftops. This was a fully developed urban civilization built from adobe, functioning for nearly 2,000 years. In the American Southwest, the ancestral Pueblans began constructing adobe and stone masonry structures around 1000 CE and reached their architectural apex at sites like Chaco Canyon around 900 to 1150 CE. Pueblo Bonito at Chaco Canyon contained over 650 rooms and stood 4 stories tall. It was built primarily from sandstone masonry bonded with adobe mortar, with adobe brick used throughout the interior partitioning. These structures were not temporary shelters. They were engineered, multi-generational urban infrastructure built to house a complex society. The pueblo I mentioned at the opening of this video, the one continuously occupied for 900 years, is Taos Pueblo in New Mexico, which is still inhabited today and is a UNESCO World Heritage Site. The walls of Taos Pueblo's north house, some of which are original adobe from the original construction period, are still standing, still structurally sound, and still providing the same thermal performance they provided in the 14th century. Adobe, with proper design and basic maintenance, does not have a service life. It outlasts the civilization that built it. In the Old World, the city of Shibam in Yemen, sometimes called the Manhattan of the desert, contains multi-story adobe tower houses dating from the 16th century, some of them standing 9 stories tall. The tallest adobe buildings on Earth. In Mali, the Great Mosque of Djenné, the largest mud brick structure in the world, was originally constructed in the 13th century, has been rebuilt and continuously maintained, and still functions as an active mosque today. The annual replastering of this structure by the community is itself a UNESCO-recognized cultural practice. The pattern across all of these examples is consistent, where adobe is used with appropriate design for climate and loading, where the base of the wall is protected from ground moisture, where the top of the wall is protected from rain penetration, and where maintenance is performed when needed, the material performs indefinitely. The buildings outlast the civilizations that built them. Part 3. Why Adobe disappeared from American construction. Adobe did not disappear from American construction because something better replaced it. It disappeared because something more profitable, more scalable, and more compatible with industrial supply chains replaced it. And the replacement happened very fast. Before World War II, adobe construction was standard practice across the American Southwest, not just in indigenous communities, but in Spanish colonial and later American territorial construction. Adobe churches, government buildings, private residences, and commercial structures were built throughout New Mexico, Arizona, Colorado, and California using local earthen materials. The territorial style of architecture, which defined the built environment of the region from the 1850s through the early 1900s, was adobe with brick or milled wood trim at the parapets and window surrounds. Then, the post-war construction boom arrived. The GI Bill generated demand for hundreds of thousands of new homes in a short period. Prefabricated lumber framing, standardized dimensional lumber, plywood sheathing, fiberglass batt insulation, gypsum wallboard, and asphalt shingle roofing were designed as a system that could be built quickly by relatively unskilled labor, using materials manufactured at scale and shipped anywhere. The system worked. It produced housing fast, and it required the purchase of every component from a supplier. Adobe required almost nothing from a supplier. The soil came from the site. The straw came from a nearby field. The labor was the builder. The molds were scrap lumber. The curing energy was the sun. There was no supply chain, no distribution margin, no repeat purchase cycle. For an industrial economy trying to build a housing market, Adobe was not a competitor to beat. It was simply irrelevant because no one could figure out how to monetize it. Building codes accelerated the transition. As standardized building codes spread across the United States after World War II, they were written around the materials and methods of industrial construction. Dimensional lumber, concrete, fired brick, steel. Adobe was not in most model codes, which meant it required special approval, engineering review, and variance processes that added cost and time. In most jurisdictions, building adobe legally required more money in permitting and engineering than it saved in materials. The regulatory environment made the cheaper material more expensive to build with. The result, within one generation, was that the knowledge of how to mix, cast, and build with adobe moved from standard practice to folkcraft to historical curiosity. A builder in 1940 in Santa Fe knew how to make adobe. A builder in 1970 in the same city probably did not. The knowledge did not go anywhere. It was simply not transmitted because the economic incentives for transmitting it had been removed. Part 4. What NASA found and why it matters. In 2021, researchers at NASA's Jet Propulsion Laboratory and collaborating institutions published work examining construction materials for permanent human habitation on Mars. The constraints of that problem are extreme. Any material used must either be transported from Earth at extraordinary cost, currently estimated at around $1 million per kilogram to the Martian surface, or manufactured in situ from materials available on Mars. The energy available for manufacturing is limited. The labor available is limited. The material must provide structural integrity, thermal performance, and radiation shielding. Martian regolith, the loose surface material of Mars, is a mixture of iron oxide dust, silicate minerals, and perchlorate salts. It is not identical to terrestrial soil, but it shares the most important characteristic of Adobe-suitable Earth. It contains fine particles with cohesive properties when mixed with a binder and formed under pressure. The JPL research examined whether Martian regolith could be mixed with available binders and compressed into structural bricks with sufficient strength for habitat construction. The answer was yes. Compressed regolith brick, the Martian equivalent of Adobe, achieved compressive strength sufficient for single-story habitat construction. The research further noted that a thick wall construction approach, the same design logic as traditional Adobe, would serve dual purposes on Mars that it serves on Earth: thermal mass to moderate extreme diurnal temperature swings, and radiation shielding against Martian surface radiation levels, which are significantly higher than Earth's due to the thin atmosphere. A thick earthen wall addresses two of the most critical Mars habitability problems simultaneously, without imported materials and without manufacturing energy beyond the mixing and compression process. What the JPL research represents is an independent engineering validation, conducted without reference to tradition or history, arriving at the same conclusion that 9,000 years of human building practice already demonstrated. When you remove the economic distortions of an industrial building materials market and evaluate the problem on pure physical performance, earthen brick is the optimal material. The engineer studying how to house humans on another planet found the same answer the Neolithic farmer at Çatalhöyük found. That is not coincidence. That is physics. The thermal performance data from the JPL work, which modeled thick wall earthen construction against Mars's temperature profile, showed interior temperature stabilization within a range compatible with human comfort during the Martian day-night cycle, without continuous active heating. On a planet where nighttime temperatures drop to -80 degrees Celsius, a thick Adobe wall provides meaningful thermal buffering. On Earth, where the problem is far less extreme, the performance margin is correspondingly larger. Part 5. The mix formula and casting process.
When we tap it,
the process of making Adobe brick has not changed in any meaningful way in 9,000 years, because the physics of the material have not changed. Here is exactly what you need and exactly what you do. First, the soil. Not all soil is suitable for Adobe without amendment. The ideal Adobe soil contains between 15 and 30% clay by volume, with the remainder being silt and sand. Too much clay and the brick will crack severely as it dries, because clay shrinks when it loses water, and the shrinkage stress exceeds the tensile strength of the matrix. Too little clay and the brick will crumble, because there is not enough cohesive binder to hold the aggregate particles together. The field test for clay content is simple. Take a handful of moist soil and squeeze it into a ball. Drop it from waist height onto a hard surface. If it holds together and flattens without shattering, the clay content is adequate. If it shatters completely, add clay. If it cracks deeply on drying, reduce clay by adding sand. Most residential sites in temperate climates have sufficient clay content in the subsoil below the topsoil layer. The topsoil contains organic material that weakens Adobe, so you dig below the organic layer, typically 6 to 12 inches, to reach the mineral subsoil. That is your raw material. It is under your feet right now. The mix. For standard Adobe, combine 4 parts soil with 1 part fine sand. This reduces shrinkage, cracking, and add chopped dry straw at approximately 1 to 2% by volume of the total mix. The straw is critical. It does not add compressive strength, it adds tensile strength. Without fiber reinforcement, dried Adobe is brittle under lateral loading. With fiber, the straw bridges microcracks and distributes stress across the matrix, dramatically improving the brick's resistance to the kind of differential settlement and minor impact it will encounter in service. Traditional builders used wheat straw, barley straw, dried grass, or animal hair. Modern builders can use the same materials or chopped fiberglass fibers, though straw remains the most effective option by cost and availability. Add water gradually until the mix reaches the consistency of thick peanut butter. It holds its shape when squeezed but does not crack when pressed. This consistency is called plastic. Too wet and the brick will slump in the mold. Too dry and it will not consolidate properly and will be full of voids. The molds. Traditional adobe molds are open wooden frames without a bottom, a simple rectangle of 2x4 lumber screwed at the corners. Standard adobe brick dimensions are approximately 10 inches wide by 4 inches tall by 14 inches long, though dimensions vary by region and tradition. The important constraint is the 4-inch maximum thickness. Thicker bricks dry unevenly, with the interior remaining wet while the exterior skins over, leading to internal cracking. Wet the mold before each use to prevent sticking. Pack the mix firmly into the mold, pressing it into the corners. Strike the top surface flat with a board. Wait approximately 5 minutes, then carefully lift the mold straight up. The brick should hold its shape cleanly. If it slumps, the mix is too wet. If it cracks immediately, the mix is too dry. Set the unmolded brick on flat ground in a location that receives full sun and good air circulation. Curing. Adobe cures by drying, not by chemical reaction. The timeline depends on climate. In a hot, dry, sunny climate, the conditions under which adobe has historically been most used, bricks are typically dry enough to handle after 2 to 3 days and reach full structural hardness after 2 to 3 weeks. In more humid or cooler conditions, curing takes longer. The bricks should be turned on their sides after the first day to allow the bottom face to dry evenly. They can be stacked for storage after full cure. Material cost. If you have suitable soil on your site, zero. The mold costs approximately $12 in lumber. The straw costs approximately $10 per bale, and a bale makes several hundred bricks. The water comes from a garden hose. For a garden wall, a raised bed surround, a small outbuilding foundation, or an outdoor oven, the projects for which a homeowner can reasonably use adobe in a weekend, the material cost is effectively nothing. The labor is the entire investment. One important design note: the base of any adobe wall must be protected from ground moisture. Adobe is highly resistant to liquid water applied to its face. The dense clay matrix sheds water effectively, but it is vulnerable to capillary moisture wicking upward from saturated ground. Traditional builders set adobe on a stone or burned brick base course that interrupts capillary rise. The top of the wall must be protected from direct rain impact with an overhang or a lime plaster cap. These two details account for the majority of adobe failures in the historic record. Get the base and the top right, and the wall itself requires almost no other maintenance. Part 6. What the building industry does not want you to calculate. The average cost of exterior wall construction using standard wood frame with fiberglass batt insulation in the United States in 2024 runs between $12 and $18 per square foot for materials and labor. For a modest single-story home with 1,500 square feet of floor area, the exterior wall area might be 1,200 square feet. At $15 per square foot, that is $18,000 in wall construction cost. Adobe, built owner labor with site-sourced material, costs approximately $0 per square foot for materials and whatever you value your own time at for labor. The thermal performance over a full year in a climate with significant temperature swings equals or exceeds the wood frame wall. The service life, with appropriate design details at base and top, is measured in centuries, not decades. The building industry does not want you to run this calculation because the answer removes an $18,000 line item from a construction project and replaces it with a bag of straw and your own labor. This is not a niche application for rural homesteaders or off-grid enthusiasts. Adobe construction is currently regulated and permitted in New Mexico, Arizona, California, and several other states under specific Adobe building codes that have existed for decades. The New Mexico Adobe and Rammed Earth Building Code has been in continuous existence since 1991. It is possible to build a permitted, code-compliant, insured, mortgageable Adobe home in these jurisdictions right now. The knowledge is not lost. The regulatory pathway exists. The material is under the ground outside your house. What is missing is not the material, not the code pathway, not the historical precedent, and not the engineering validation. What is missing is the transmission of knowledge that was interrupted 1 generation ago. When the industrial building materials industry found that the most cost-effective wall material ever used by human beings was also the one that most effectively excluded them from the transaction. Closing. 9,000 years ago, someone at a site in what is now Jordan mixed clay soil with water and straw, packed it into a mold, and set it in the sun. The brick that came out of that mold performed well enough that the technique spread across the ancient world, was independently rediscovered on multiple continents, housed some of the most sophisticated urban civilizations in human history, and is still standing in buildings occupied today. 2 years ago, engineers at NASA's Jet Propulsion Laboratory ran the same calculation from first principles for the problem of housing humans on Mars. They arrived at the same answer: compressed earthen brick, thick walls, thermal mass, zero manufacturing energy. The oldest building material on Earth is also the most rational building material for another planet. The reason you were not taught this, the reason it does not appear in home improvement magazines or on the front page of building supply websites is simple. You cannot buy it from anyone. It is under your feet. And an industry that generates $18 billion a year selling you wall systems has no financial interest in reminding you that the optimal wall system has been free for 9,000 years. A wooden mold, subsoil from your own site, chopped straw, water, sun. That is the construction material that sheltered the first cities, that stood 9 stories tall in Yemen, that NASA is designing for Mars, and that you can be making in your own backyard this weekend. The mix has not changed, the sun has not changed, the physics have not changed. The only thing that changed is that someone decided there was more money in making you forget.